welcome back everyone. So we're going to look at examples 5, 6, and 7. And then we've got some additional examples below, but these are just going to be using the limit definition of the derivative. So those I think I'll leave for you to do on your own. But I do want to talk about kind of the interpretation in context for the derivative. So for number 5, we've got a given function. 6, we've got a table. And 7, we've got a graph. So different variations on how we can use the derivative to describe some sort of phenomena. So 5 says the cost of producing X ounces of gold. So we've got X ounces of gold from a new gold mine is C equals F of X dollars. So our function is a function of ounces. So if I know the number of ounces of gold, I can figure out what the cost of producing that is going to be. So this is a typical style of a cost function. So it says, what is the meaning of the derivative f prime of x, and what are its units? So units are the easiest way to kind of start, probably. So let's just note that the derivative can be thought of as the ratio dy over dx or df over dx, and that tells us the ratio. That tells us what the unit rate is going to look like. So f, again, is going to be the cost in dollars, and x is going to be ounces of gold. Right, so it's going to be dollars per ounce. So this is going to tell us what the rate of the rate of change of the cost of producing X ounces of gold is at a particular weight. So, okay. So we can put that in words. So f prime of x is the rate change of the cost for producing X ounces of gold. And what we normally call this, if we take a cost function and find its derivative, so we have the derivative, so prime, we can use prime notation. So the derivative of cost is typically called the marginal cost. So again, this is telling us how the cost is changing as we're producing a certain number of ounces of gold. So then what does f prime of 800 equals 17 mean? So the rate change of producing 800 ounces of gold $17 per ounce. And so if this were a real cost function, what we want to figure out is what is the most that we can produce that is going to yield the smallest cost per ounce, right? We want to lower our cost per ounce. If this were a revenue function, it would be the reverse. We would want to maximize the revenue per ounce. So finding minimum and maximum values is what we're going to explore in chapter 3, but we're going to be able to find those minima and maxima values, those extrema, by using the derivative. All right, so we've got our cost function there. So now we've got a temperature function. So we've got capital T of T is the temperature in South Pasadena. We're going to do it in Fahrenheit. At T hours after midnight. So this is going to be measuring from midnight on a particular date, September 15th. The table shows the values of the function recorded every 2 hours. So what is the meaning of T prime of 10? So T prime of 10, so again, let's think of our units, right? So T prime of T, which is D capital T over D little t. Well, the differential of temperature is temperature in Fahrenheit, and then the differential of time is just going to be time. In this case, it's going to be hours. So we can update that. Let me zoom in a bit here. So degrees Fahrenheit. So this is going to be the change in temperature per hour, right? So the rate of change of temperature after 10 hours from midnight is going to be what T prime of 10 is. So T prime of 10 is the rate of change of the temperature 10 at 10 hours past midnight. Okay. And then it says estimate this value from the table. So now we get another kind of interesting look at how we can estimate the derivative. And so we don't know what the actual function is. So our only recourse then is going to be to use that slope of the secant line, the difference quotient of what we normally take the limit of. So if I look at 10, right, we've got symmetric data. So we've got from 8 to 10 and 10 to 12. And so I could take the derivative from the left, which would be between 8 and 10. So as I'm approaching 10 hours, I could take the derivative from the right. So as I'm going past and kind of working backwards, or I could do it symmetrically between 8 and 12. So let's look at those different estimates here. So T prime of 10 is approximately, so if I do it from the left, that would be 81 minus 72 over 10 minus 8, which is going to be 9 over 2. And note that's 4.5 degrees Fahrenheit per hour would be our units. So the approximate rate of change of the temperature would be 4.5 degrees Fahrenheit per hour. But I could also have done it from the right. So that would give us 7 over 2, which is 3.5 degrees Fahrenheit per hour. So again, different answer, but they're both estimates. They're both going to be estimates that we want to use. And we don't really know which one's going to be the more accurate one, because we would need to know more information about the function. And then finally, if we wanted to do symmetrically, we could do 88 minus 72 all over 12 minus 8. So I could do it at even time intervals beyond 10 to the right and to the left. So that's going to give me 16 over 4, which is 4 degrees Fahrenheit per hour. So again, we don't have specific information to know which one of these is going to be better. You might think, well, 4 is right in between both of those upper and lower estimates. So maybe 4 is better. So again, we don't really know exactly what is going to give us the best approximation, but all three of these seem pretty good, right? They're all within a degree Fahrenheit of each other. All right. So going to number 7, 7's a similar problem. So the quantity of oxygen that can dissolve in water depends on the temperature. So thermal pollution influences the oxygen content of water. So the graph here shows how oxygen solubility varies as a function of the water temperature. So as temperature increases, solubility is going to decrease, it looks like. So oxygen solubility. So keep in mind the units here. So for these application problems, we've got milligrams per liter is the y-axis. So it's this ratio value, and then temperature in Celsius now for this example. So it says, what is the meaning of the derivative s prime of t? What are its units? So I'll let you kind of decide what you think that is. The meaning of that derivative and its units based on our previous examples. But what I do want to discuss is kind of estimating the value of s prime of 16. So we can see that s of 16 is going to be somewhere between 12 and 8, right? So we know it's that s of 16 is somewhere between 12 and 8. And so what we want to do to estimate that, again, is just to take two values that we can use that are going to be useful measures. And we typically want to get as close to 16 as we can. So I could take the points at 8 and 16, and again, find the slope between them, the rate of change between them. Or I could do it from 16 to 24. Our slope is decreasing, so you can choose which one you want. So note s prime 16 is approximately s of 16 minus s of 8 all over 16 minus 8, or s prime of 16 is approximately s of 24 minus s of 16 all over 24 minus 16. You can estimate those values yourself. Or, again, if you wanted to, because we have symmetric time measurements on either side, could do s of 24 minus s of 16. Oh, sorry. Minus s of 8 all over 24 minus 8. So any of those three could work. And again, s prime is going to be the rate of change of the solubility per degree Celsius. So it's going to be the rate of change of milligrams per liter per degree Celsius. So, okay. So I think we're going to stop there. Again, 8 you can do on your own just using that limit definition of the derivative. So this is going to end 2.1. So interpreting the derivative. And again, this interpreting of graphs, tables, functions, this is going to be key for our entire course, is moving between those different representations of data. So until next time, send me an email if you have questions or come by the office hours. And until I see you again, take care.